In this video, we want to talk about parallelism. Now, this will be the only time in this video, hopefully, where I have to say this word, since it is quite a mouthful. Okay, so in the last few videos, we've talked about concurrent and sequential evaluation of code. We have talked about how, for example, DeepSec works in order to deeply sequentially evaluate something, and we have looked at concurrency and STM. Something that we haven't talked about is parallel execution. Now, you might say, well, if I want to have parallel execution, I could just use a concurrent system doing parallel work, and you'd be right. But there is an easier way of doing parallelism. There's that word again. And I want to show you how that works. Okay, so in a dream world, our parallel workflow looks like this, where every black dot is a computational unit, so one computation that we can do atomically. And, you know, in a perfect world, we could just spawn different threads, basically, of computational units that have some sequential relation. And we could, in this case, just spawn 5 threads. Every thread does one sequential process here, and in the end we combine everything. That's great, right? Well, if we look at real-world problems, we might see that it looks like this, where the sequential relations of certain computational units is much more, well, much more complicated than just having perfect parallelism. So let's analyze this. In this case, we have some sequential relations between computational units that can be evaluated in parallel. So for example, the red and the blue one can be evaluated in parallel, or the orange and the purple one, and also the green one in this case. So that's quite interesting. But we also see that we have these computational units here that have more ingoing edges than just one. And that's a problem, because those force the sequential evaluation of multiple parallel threads. And that, of course, is a very hard thing to model in a concurrent system. Because then you need to add new flags and new barriers for your threads to have some synchronization on. And that might completely diminish the performance you can get out of your system. So, we want to ask the question, is there a modular composition of parallelism? So the question here is, can we, in a modular way, compose such a parallel program so that all of these sequential relations are well satisfied? And then that leads us to another question, which is, can we even abstract computations and their sequential relations? Well, yes, we can, and the answer is parallel Haskell. In the video on concurrency, we have seen concurrent Haskell, but this is parallel Haskell. But it's not part of the standard Haskell environment, so we have to install it with Cabal, for example. And then we can import it like this. So, before we go into the documentation, let's talk about two very important things. The first one is the so-called Eval monad. It stands for a computational unit. It can be parallel or sequential, and the evaluation is managed by the runtime system. That's very important. So that already gives us a notion for a computational unit, that's great, and we already have the information whether it is parallel or sequential, all within a monad. Of course, a monad is great because then no side effects can happen. So now the question is, how can we compose them? And that's why we have this very simple type, which is a strategy. It takes some value A, and then, well, it's basically a function pointing to some eval monad. And since we know that functions can be composed, of course, This makes it possible to compose the creation of an eval. And not only that, we can make interleaving evals and all of that stuff. Really cool stuff. And the nice thing is that since a strategy should not be evaluated right away, it's just a, huge function sometimes, it defines how to evaluate data, but it does not define the data itself. So we could define a strategy and then just later apply it to, some data. The great thing about this is that we can build very, very abstract strategies for evaluation, where we basically tell the runtime system of Haskell to deep evaluate some stuff and then to sequentially evaluate, so evaluating to weak hat normal form, some other stuff, and then putting it together in a parallel process, for example. And then we can apply it to some data. Okay, so what functions or what values are important for strategies? Well, the two most important ones are rpar and rsec. We will look at their application in a second, but those are the ones that we use, the basic building blocks in order to build those strategies. Then there is rdeepsec, which works like rsec, but as you can see, we need an NF data for this, so this will do some deep evaluation. And then, after we've built our strategy and after we've built our eval monad, we can use run eval in order to get the value out of the monad. Okay, so here we want to look at some examples of how rpar and rsec work. So let's look at this, where we run the eval on an eval monad that looks like this, where we have two computations, f of x and f of y, that we do in parallel. And as we can see, it's the thing that we actually wanted is happening. Both happen in parallel. But the very important thing is that the return happens before anything else. And that might be confusing. Of course, it is somewhat confusing. Why do we return before we compute? But that's of course because Haskell is lazy. And yes, the sparking of new computations, and you will see why I call it that in a second, is also lazy. So that is something to keep in mind. Even though we build strategies, those strategies are just applied lazily. So this shows us that in this case we return the tuple, and the computations for the thunks have already started. So let's assume that the program that gets this tuple is now doing something else and waiting on some other action. Well, f of x and f of y are still evaluated in parallel in the background, basically. Okay. So now we look at how to work with rsec, because rsec now forces evaluation to weak hat normal form in a sequential manner. So here we see that for a, we still want to have some parallel execution of f of x, which is great, that's what's happening here. But then we force sequential evaluation of b, so of f of y, which is stored in b. And since we force that, the return cannot happen, because the return would need to send out the thunk of b. But we sort of disallow that. We want to have weak hat normal form for b, so that's what's happening here. And now you can do something even crazier, which is force the evaluation of a after declaring it to be parallel. So why does that work? Well, what we're doing here is basically we say, okay, evaluate A in parallel and B sequentially. After that, force the sequential weak hat normal form evaluation of A, and then you can return. You could also build this strategy where you basically declare both as a parallel execution, but then force their sequential evaluation before returning. This can be used in order to define in order to make sure that some data is evaluated before it leaves the monad. Okay, so now we want to answer the question how the runtime system actually handles the parallel computations. It is done with something we call a spark. Now, let's look at the life cycle of such a spark. Now, when we want to propose a task, we don't really create it up front, because let's think about what we actually try to achieve. What we are saying is that, hey, here is some data, here is some thunk that is unevaluated, and now please evaluate it in parallel. Now, if everything goes according to plan, we simply create that task as a spark. This spark will then be put into a spark pool of an HEC, which is a Haskell execution context. Now, that's something very abstract, but you can think of it as one HEC equals one core on your machine. Okay, but what if the task that we proposed was already evaluated? That could happen, right? You could evaluate something and then later force its evaluation with rsec or rpar. Now, in this case, we call that spark a dud, because it simply has been already evaluated and it points to some data in weak head normal form. Important, not just normal form, it's weak head normal form. And in this case, it's not added to the spark pool. Simply nothing happens in this case. Or there could be an overflow. Now, that is the biggest problem that we face when designing parallel algorithms. The problem is that the spark pool for every HEC has a fixed size, so it could overflow. And in this case, the spark simply is not put into the spark pool. In this case, we simply evaluate it sometime later, but it's not being evaluated in parallel. So think about it. If you want to spawn a lot of parallel processes, but the spark pool is full, then all of the parallel processes that you proposed after the spark pool was full, well, they will not be evaluated in parallel. So this can be a bottleneck. Okay, so let's assume that our spark was created successfully. Now, in this case, certain things can happen. Of course, the best case would be that we can convert the spark. This means that some HEC took that spark and evaluated it, and we were done. Right? That is how a spark lifecycle should go. But there are other possibilities. Since this spark now lives in a spark pool, it's not being evaluated right away. It depends on how many sparks we have. But what if our main program flow forces the evaluation of that spark before one of the HECs could take that spark and evaluate it? Now, in this case, we call it fizzled. It's not the same as with a dud. A dud was evaluated at proposing time, basically. Fizzled sparks have been evaluated after the creation, but before the conversion. Okay, so basically those are sparks that have been in the spark pool and then have been evaluated without the whole logic of sparks behind it. And then there is another way that a spark could die, basically, which is it could be garbage collected. Now, it could happen that, of course, a spark is just some deferred computation. It is some lazy stuff that's happening. Think of the tuple again. What if we have two sparks pointing to a tuple, but then we call first or second on that tuple? Now, in this case, one of the sparks will, well, be irrelevant. And in this case, the garbage collector could come and simply swipe that spark away. And that is not that bad for us because, hey, I mean, we simply didn't evaluate anything, so it wasn't that bad. But the problem is that if we create too many sparks that will be garbage collected, then actually we will basically waste our time with garbage collecting and never really get any work done. Okay, so now we've looked at how sparks work, and we will look at them a bit more in detail in a second. But for now, we want to go into the documentation of the module that we will be using. Okay, so here we are in the documentation of Control.Parallel.Strategies. Now, we have talked about most things, so how eval and strategy works. Let's talk about some functions that we can use with strategies. Okay, so one very important one is using. Using can be used in an infix style, which looks like this, where we can say, okay, we have some data evaluated using some strategy S, and that's the same thing as calling run eval, which, as we have seen before, evaluates an eval monad into a value with that strategy. So that's just a very nice syntactic way of using strategies. But then there are many more. There is also a way of composing strategies. That is the important thing that we've talked about before. We can take multiple strategies and just compose them, which is nice. Right, and then we have a lot of other functions that can be used to work with lists, for example, and also to work with lazy lists. Like here we have eval buffer and par buffer, which are of course very important for input-output or simply lists that we have to evaluate lazily. There is also something which is quite interesting. Those functions often have a chunking feature, where the list is put into chunks before it's being evaluated. We will see why that is very important in a later example. And then there, of course, are some functions for tuple evaluation and some strategic function applications, which, well, we won't be using in this video, but you can if you so desire. Okay, so that's about everything. Maybe one thing that I really want to talk about is that the API history here has changed quite a bit. As you can see here, a lot of the functions have been renamed, or they simply don't exist anymore because this done type doesn't exist anymore. You see that there is a lot of deprecated stuff in here. And not only that, there are functions in here that are actually subject to change. So it could be very well true that at some point you might look at this video here and you will realize that some things have changed. For example, here for parlist chunk, it is expected that this function will be replaced by a more generic clustering infrastructure in the future. So things could change. This is very much experimental what we are doing here, as is also indicated here. The stability is experimental. So the things could change. But I suspect that the general way of how things work will not change in the future. Hopefully, at least. Okay, so now let's look at a program which we actually want to, have a parallel execution of. In this case, we will use the Fibonacci function just to have some computational complexity. Of course, doing the Fibonacci function this way is bad. We have seen this in the infinite lists video, how we can actually improve this quite a lot. But hey, that's just how we're doing it. So we have two computations here, the 38th Fibonacci number and the 37th Fibonacci number. Those are our two computations that we want to do, and in the end we want to print a tuple built from the two results so that the evaluation is actually forced at some point. So how do you actually use Control.Parallel.Strategies in order to do that? Well, let's take a look at an example. So here we actually have the parallel version of this program, or simply the better version of this program, where we use such an eval monad in order to, well, first spark the two computations in a parallel manner, so both will be put into the spark pool, and then we force their evaluation. Now, we would not really need to do this sequential forcing here. This is not needed. I just like to do it so that I know that the result is fully evaluated, or at least evaluated to weak hat normal form, but for ints that basically is a normal form. I just like to know that the data is evaluated before it leaves the monad, which it of course does once you call run eval on this. Right. So let's compare both. Let's see how those two are working. Okay, so here we have the two files, fast and slow. Slow, of course, is the slow version and fast is the fast version. How do you compile this? Well, we need to use the threaded flag. Of course, because this is now a multi-threaded program, we want to have multiple Haskell execution contexts, so we have to use threaded. We will also use some other flags, RTSOpts and Eventlog. I will use those in order to, visualize some stuff that is happening, and you will have to use these flags if you want to analyze your programs, which you will need to do. We will talk about that in a second. And we will use the make flag just for good measure. We will not use any optimizations because that could, sort of change how stuff gets evaluated and make the comparison a bit unfair. Okay, so let's time the execution that it takes for slow to run. We will use the RTS flags of -n, so that all of my CPU cores are being used. I have 4 cores on my system. Of course, for the slow program, this makes no difference at all. Of course, because the slow program doesn't have multi-threading. I just want to use the same options for both programs so that the comparison is 100% fair, since some of the garbage collection can also happen in parallel. Okay, so now we're running the slow program. It took us 6 seconds in order to do it. So let's call the fast program, of course, with the same options enabled, with multi-threading enabled, and we see that it is actually faster. Okay, so that's great. So we actually have a speed up. The parallel processing worked, but let's look at this stuff in more detail. What we now want to do is we want to call fast with another flag called -s. And -s will give us a summary of the garbage collection. So we've got quite a lot of stuff here. So let's look at what happened here, because here is quite a lot of stuff. So here is some stuff that was allocated in the heap. We don't really care for that because this is not really about the garbage collector. This is about how our sparks worked. And if we look down here, we see some statistics on the sparks. Okay, so we had 2 sparks. That totally makes sense because we had 2 calls to rpar, which sparked new sparks. And here we see a statistic on how stuff happened. So one got actually converted, so an HEC converted it, but another one fizzled. Well, why is that? Well, that's because at some point, of course, one spark was evaluated before the other one was evaluated. So the last one, which wasn't converted fully, then got simply converted by our main thread, basically. So it fizzled because it wasn't as fast as the other spark. Okay, so here we have some timing data. So the elapsed time is the real time, which we are interested in, and it took us, again, 3.7 seconds. Very important, the MUT, the mutator time, is the time that your program actually took to run code. So all of the other time that is spent on the garbage collector, the GC, on init time, which is just some initialization, which we really don't care about, and some exit time, which the program takes in order to exit. So that's why we often look at this productivity down here. The productivity, especially of the total elapsed time, is the ratio between the time our mutator uses and the garbage collector uses. Again, the mutator really is our program. So this productivity, of course, should be as high as possible. 100% if that's possible. It isn't, because the garbage collector has to do something at some point. So that is really important. But we will see that this productivity measurement actually can become a problem. Okay, so I want to go even deeper into analyzing this program, which is why we will call it again, but now with the ls flag. Okay, so let's run that, and it will take some time. Okay, now a new file has popped up, which is fast.eventlog. And now we will use a program called ThreadScope in order to analyze this. Okay, so here we are in ThreadScope. ThreadScope is a program that will visualize the event log that we just created. You can download this program on the GHC website. I will put up a link in the description. So, when you analyze the event log, we have this chart to go by, and here we have some keys, but I will explain the most important aspects. So when we want to actually take a look at how good our parallel workload worked, we have to look at this activity graph here. Activity tells us how many of the multi-threaded resources that we had were actually used. So I have 4 cores on my system, so -n got transformed into -n4, and -n4 means that we are using 4 cores on my system. Well, those 4 cores are represented by HEC 0 to 3, so those are the execution contexts which roughly translate to 1 core on my system. Of course, we only had 2 things that happened in parallel, so only 2 of the cores got active and the other ones, well, they did nothing. So this is reflected in the activity here, because up until this point, so here in the first roughly 2 seconds, well, yeah, roughly 2.25 seconds, we had perfect parallel workflow, since as you can see, we basically use all of 2 cores in this part here. So this is really cool. But it's not really hitting that dashed line perfectly. Why is that? Well, let's zoom in. And when we zoom in, we see that, hey, we actually do, but there's some funky stuff going on here. What is that? Well, at those little points, actually one of the execution contexts makes a request to the garbage collector. And then the garbage collector, for a very short amount of time, extremely short amount of time, got active. And at that point, we then resume the execution. And that is something that we can't really get rid of. So that's just happening. That's just something that happens, and well, too bad. But hey, our productivity is still great because we still have almost 100% productivity. So our mutator worked most of the time, which is exactly what we want. Okay, so here we observe that at this point, one of the cores was finished. So that was probably the execution of the 37th Fibonacci number. So this execution still had to go on for a bit, and that's where we see that the activity graph is actually plummeting. Okay, so here we can actually enable more traces like spark creation, conversion, and pool. The sad thing is that for this example here, it doesn't really make sense. It doesn't tell us anything. But in a later example, we will see that this is, well, really helpful. Okay, so I also want to turn your attention to this key here because it actually tells you everything, but it's a bit hard to understand because not all of the things you see here are actually applicable to every single graph. So for this main graph here, you basically only care for running, GC and GC waiting, and then some of those things like creating a thread and doing some GC requests. But then for stuff like spark conversion, we actually care for these legends here. So basically for creating a spark, the dot spark, the stuff that we've already talked about. Okay. So that was a very simple program that got a speed up, a significant speed up by parallel execution. Let's look at a bad example. Okay, so here we are in another program which does the following. We have some list that, well, is lazy in this case, but we don't really care, and we want to do a mapping on it where we simply add +1 to every single element. Then we want to force the evaluation of this mapping, and then we want to get the last element of this list. So with last of this X, we actually force the deep evaluation that we wanted to declare here. Okay, so as you might expect, doing all of these calculations here takes some time because we have quite a few elements to go through. So we might speed this thing up by having parallel execution, right? So something that we can do is we can use the parmap function, which in the end will spark parallel sparks that evaluate the list. Parmap is something that you can find in the documentation. It basically creates a parallel mapping on a list. Great. So let's look at that and let's see if we can get a speed up this way. So we will use the same flags as before. And we will compile. Okay, so here we're compiling it. And let's simply call slow. Again with -n, and let's get a GC summary of the whole thing. Oh wow, that was quite quick. Took only 2 seconds, but as we can also see, the productivity is way down because we had to do a lot of garbage collection. Actually, you can see here that the mutator only took half a second, but the garbage collector was the one that took a lot of time. Okay, so let's look at fast and see if this gives us a bit of a, speed up. But this doesn't look good. Wow, this didn't look good at all. It actually took us 8 seconds. It took much longer. Well, why is that? That is very weird. So first of all, something to consider here is that the GC, the garbage collector, took a long time here. It took much longer than the other one. And also our mutator time was pretty bad. Why is that? Well, if we look at the number of sparks that we have, we see that we have double the amount of sparks that we actually had elements in the list. Why is that? Well, because we used the parmap function wrong. And that is something that might happen to you too, and I just want to basically warn you. So what's the problem here? Well, parmap is already spawning parallel sparks for every single element in the list. So we don't need to spark another parallel spark. That makes no sense at all. So actually we can use our sec here because we don't want to further parallelize something which has been parallelized. That makes no sense. So we use our sec here. Okay, so let's recompile this and maybe we get a speed up now. That would be great, right? Okay, so we're running it, and as you might see, well, no. Actually, that wasn't the problem. Well, that's strange, isn't it? Why does it take so long? Well, as we can see here from the statistics of our sparks, we see that a lot of them got converted, which is nice, but also a lot of them overflowed. So this means that the garbage collector had to work quite a lot in order to use those overflowed sparks and put them back somewhere and all of that stuff. It actually is quite a lot of work to do here in order to create all of these sparks. Because when we create a lot of sparks, the garbage collector has to do a lot of work in order to keep everything tidy. So we see that we're, a bit faster than the slow program was, but let's call the slow program again, just so we have a reminder of how fast it is. It only takes 2 seconds. So here we have a slowdown of, a 3-time slowdown basically. That's not good. And as we can also see here, the productivity is way down. The productivity, it's actually not that bad. That's the funny thing here. The productivity is roughly the same. But the problem is that because we have a parallel workflow and we're creating all of these sparks, that is actually time that our mutator takes in order to, basically do anything. So that is something to keep in mind. Creating sparks, even though it is advertised as being lightweight, is not that lightweight once you want to create a lot of sparks. That is actually a huge problem. So okay, let's run the fast program again, this time with ls, and let's get the event log of this program, And let's see if we can further analyze the problem here. Okay, so here we are in ThreadScope, and we will take a look at the event log of this fast program. Well, it's not that fast as we have seen. So, just looking at this diagram, we see, wow, there is some horrible stuff happening, especially garbage collection times, which take, well, huge amount of times off our execution. Especially here at the end, where basically we don't do any processing anymore, but only do garbage collection, and quite a lot of it. So that's very fascinating. So let's maybe go into here, and we see that the activity diagram actually tells us that we use, that we basically use 2 cores of the cores that we have available, but that's not true. Because if we zoom in, we see that, well, we are actually using all of them. We have a perfect utilization, but this utilization is often stopped by a huge garbage collection time. We see here that often we remain, I think, longer in the garbage collection than in the actual computational time. So that is a big problem, of course. And if we zoom out, we see that, well, the other garbage collection times that we have here are so horrible that basically everything stops. The only thing that's happening anymore is the actual garbage collection. So let's analyze this further by using traces, and let's go into Spark creation. And here we see that, whoa, what's happening? Only one of the execution contexts is actually creating anything. And that's, funnily enough, everything that it's doing. That's the only thing that it's doing. It's just spawning new sparks all the time. And we can see here that at first everything runs fine, but then we have this case where, strangely, we seem to have those red sort of spikes. What does red mean? Well, if we go into key, we see that those are the overflowing sparks. So here, the creation was actually stopped because the pool was full. Okay, so let's analyze this by not looking at the creation, but the pool. And here we see that the other execution contexts didn't have any pool growing. They just didn't have any sparks. The only execution context that had some is HEC2. So what's happening here? Well, in order to analyze this, we will also enable spark conversion. And we will see that, hey, HEC2 never converted a spark. It was all the other execution contexts. This is called work stealing. It's called work stealing because this pool basically was the work that HEC2 should make, but it never had the time to actually do it. It always created new sparks. So actually, the other execution contexts took over and basically converted the sparks. But here's some funny stuff is happening. So at first, the pool size was quite okay. And if we look at the creation again, where is it? We see that, yes, we were totally able to create sparks however we wanted. That's because here we had basically long times of garbage collection where the other execution contexts were able to do some work and to keep the number of sparks in this pool rather low. But then we are at this point where we have this huge spike. And that is especially at this point where we also see that the garbage collector ran crazy. And that is where huge problems arose, because we see that now we are topping off the number of sparks we can have. And as we see, that is after the garbage collection time, that is the point where we are overflowing. So that is the point where we basically keep this pool at a constant high, except for this little thing, but we keep it at a constant high and we never go down. So again, this execution context is just always preoccupied with creating new sparks, while the other execution contexts try to work. But they are not really able to work because the garbage collector was preoccupied with garbage collecting. So this explains the horrible performance that our program has. So the takeaway is that if we want to create sparks, if we want to spark some computation, then this computation should be expensive enough. And that was something that we didn't have here. Simply incrementing a number, that's not expensive to do. So actually creating the sparks was the real problem here. Another problem was the size of the list. We had a huge list that we wanted to completely execute in parallel. Well, that was of course stupid because we couldn't fill all of those pools with all of the elements. So that was just a wrong choice on our part, of course. Okay, so let's look at a more involved example where we actually get a speed up and try to run this fine line between having too many sparks and not enough. Okay, so for our last example, we want to look at numerical integration. So we basically want to compute the area underneath any given function. And we will use the most basic version of doing that. We will use the rectangle rule, which is this one. So basically, if we look at this picture, what we will do is we will have some function and we will create these rectangles underneath it. And then we will basically sum those areas up. Of course, this isn't the perfect way of doing integration, but hey, that's what we're going to do. Of course, we want to be a bit precise, so we will use very narrow rectangles here. Now that's of course great, but that means that we have a lot of workload which could be done in parallel, of course, because summing up those rectangles or actually computing those rectangles, well, that can be done in parallel. And it's always relative to the function that we actually need to compute. So if that function is just very expensive to compute, then parallel workload might work here. Okay, so here we are in our program. This program will create an integral of this function f of x here, which is just a combination of a bunch of trigonometric functions, just so that we have some workload going on. So how does this function work? Well, it takes the function to create an integral of, and then has a stepping length. That stepping length is the width of the rectangles that we create. Then of course it has a start and an end point for the integral. Okay, so what we do is we compute that rectangle and then we recompute the new points and then we do the recursive call to this integral function. Great. So how do we create a parallel workflow within this function? Well, one thing that we could do is to spark this computation and then to spark the recursive call. We could do it like that, but there is a better way. Let's rewrite this program so that it uses this, a step list. This step list will be the coordinate points for our rectangles. The great thing is that after we've created these steps, they work just like they worked before. We can now basically compute everything with just one mapping. And this mapping will map a coordinate or a sort of width specifier, if you so choose, to the rectangle calculation that we want to do. Okay, so this will actually be our slow program. Now the question is, how do we create a parallel workflow out of this? Oh, right, and something I forgot to mention is that after we have created all the areas of the rectangles, we of course have to sum them up. We use the strict version of fold L in order to not have that many thunks, right? That is something that we talked about in the episode on strictness. Okay, so how do we create a parallel workflow? Well, we have a mapping here, so why not use parmap, the parallel mapping? Well, of course, we have seen before that this could be a problem if we have too many sparks, too many elements in the list steps, is not good for the spark creation. The spark pool will overflow. So we create something else, and that is this function. Nothing much has changed. The only thing that has changed is this portion here, using parbuffer 100. What is that? Well, parbuffer was the buffer function or the chunking function for a lazy list. And of course, steps is lazy. So the mapping here is also lazy. So now we want to defer this to a parallel execution with parbuffer. But what is done here is that we create chunks of 100 elements that are then sparked in parallel. That's basically what we do. And of course, we don't want to spark them again in parallel, so we use rsec here. So as you can see, we didn't have to change much. We really just put this code after our mapping, and this is everything that we did. Crazy. So let's compile those. Again, we will use threaded, we will use rtsopt, and we will use Eventlog, and we will use make. Okay, so fast is our parallel program, and the slow program now is called stepping, because that was the one that introduced the step list. So let's analyze this. We will call slow, we will call stepping with -n and -s, and see how long that takes. Now the function is a bit expensive to compute, so it takes some time, and as we've seen here, yes, it took us some time. It took us 5.5 seconds. Okay, great news is that the garbage collector didn't need to do much, so we had a lot of productivity here. So now let's do the same for our fast program and see how fast that actually is. And as we can see, we have a considerable speed up. Now we only took 4 seconds. Another important thing is that when we look at the sparks, here we have a lot of sparks, and most of them got converted. So if we were to create a conversion rate of sparks, this is actually really good. We had none overflowing, which is absolutely great. That's because we did the chunking. We had no dots, which is fine, and we had some garbage collection and some fizzle sparks, but we don't really care about that, because if you take the number of those and compare them to the number of converted sparks, that's of course totally negligible. Okay, so the productivity wasn't better than it was for the slow program, but hey, we were still faster, and that's because our actual mutator was much faster. We took 3.7 seconds here, while we took 5.4 seconds here. Of course, we also doubled the time that our garbage collector took, but that's again negligible, because the speed up that we get from the parallel execution was enough. So now you might ask one question, but we could improve the slower program. We could, because if you look, if you look at the source code, then you see that here we create a mapping, and after that, the result of the mapping we throw into this fold. But we don't have to do that. We could basically throw this whole thing into fold immediately. So let's do that. So that would look like this, where we now create the sum directly through the fold without a mapping. Now, of course, this now isn't that easy to convert into a parallel workflow. Of course, because now we don't have a mapping but a fold. So it would be really bad news if the folding was actually faster than our fast workflow, right? Because then that would mean that our parallel workflow makes no sense. But if we actually run this program, we will hopefully see that the direct folding is still slower. It is a bit faster than doing the mapping first and then the folding, but it's not as fast as our fast program was. Okay, so let's run the fast program again. But now let's add the ls flag in order to look at the event log of this program. Okay, so here we are in the event log of our program, and we see right away that the activity looks great. We have 3/4 constantly topped out, which is nice. But then the question might be, why only 3/4? Why not the whole thing? Well, let's take a closer look, and we can see that very often we actually top out, but then we sort of go back to 3/4. So it seems that way that some of the execution contexts that we have will stop their work. And, well, we can actually see this right here. They stop their work at a certain point. Okay, but that's not really something that we are able to very easily fix. So let's look at the whole thing and maybe try to find an architectural problem here. So if we look at the Spark creation, we see that only one execution context is actually creating anything. That makes sense. It is totally sensible for that to happen, since we call par buffer on this lazy list, and some of the execution contexts simply have to do that. We could have spawned a parallel chunking, basically, but that's not really what we wanted to do, because it could also overflow the pools, and we don't want that. So only one thread is basically creating sparks. And the conversion is done by the other three. So this is where the 3/4 actually makes sense, that 3 threads are actually working on it, and the other one is just converting computations into sparks. And then when it tries to convert something itself, it sees very often that, oh, it has already been GC'd, so I can stop there. And that is also reflected in the pool size. The pool size of HEC2 is at a constant high, basically, but it's never overflowing, which is great. The other execution contexts then do their work stealing and steal the work off of this pool. And that is giving us our parallel execution, which runs pretty nicely. There are some cases where the GC is actually, well, getting into our way, but that's not too bad. It only happened 2 times, and I don't even think that we can optimize this in any way. I think that has something to do with the runtime system. Of course, our productivity was very good, and that is something that we of course want. And again, that is something that I've already talked about. It is great that we were able to convert so many sparks. As you can see here, as I said, HEC2 was the one that was spawning all of these sparks, but it was, well, only rarely converting one. Most of them got GC'd. The great thing is that for the other ones, the fizzling sparks were, well, negligible, and most of the sparks that we wanted to convert got converted in the way that we wanted. That's great. Okay, so that's about it when it comes to parallel strategies. But now a very important question has to be asked. Was it worth it? Was the work we did actually worth it? Well, having a parallel workflow makes sense for algorithms that support it. We have many algorithms that in their nature work very well when doing it in a parallel way. So for example, a Monte Carlo simulation, for example, or numerical integration, or something like Fourier transform, or something like that. That is great if you do it in a multi-threaded way. But this is not applicable to everything, right? Stream ciphers, for example, don't work. But then on the other hand, block ciphers, they would work. So, you know, it's always a question of, are your algorithms even ready for a parallel workflow? But also, having everything in parallel is not always the answer. We have seen this with the Fibonacci program. Yes, we can achieve a speedup by doing 2 Fibonaccis at a time. But as we have seen in the video on infinite lists, there are just ways of doing it much faster, even in a sequential way. And that is something to keep in mind. Okay, so that's about it when it comes to the problems of having parallel execution. Another problem that you should keep in mind is that all of the features I've shown in this video might change tomorrow. They might change in a year. And maybe, depending on when you are watching this video, they already have changed. This is an experimental feature in an experimental version of Haskell, which is called Parallel Haskell. And since it is so experimental, we don't know for sure if things will change. The experimental nature also shows when doing tests on these programs. A problem that I have observed, which I couldn't find anything on the internet, was that if I have one program running which has a very high single-threaded workload, basically occupying one whole CPU core, then this whole multi-threading system fell completely apart and didn't know what to do anymore. Because, of course, the execution contexts try to be in one-to-one correspondence with the actual physical cores. So if one of those cores simply doesn't know what to do or is simply full of work, then the balancing here basically falls apart, which makes the development of these algorithms, well, very difficult. So I'd advise you to look at this topic with curiosity, but not with the approach of using this in every program you will ever write, because it will probably not work. Okay, so that's it. If there are any questions, please feel free to leave them in the comments below. And as always, thanks for watching. You wouldn't believe how many coffees I run through making one of these videos. If you'd like to support them, you can do so on Ko-fi, where you can, well, buy me a coffee. Any support is greatly appreciated. Thank you.